Welcome everybody to the IEEE Day celebrations. IEEE Day is a unique event held on the first Tuesday of every October, where members come together to share their ideas and inspire the others to achieve their technological goals. So this year, the celebration will be held in a hybrid mode due to the COVID-19 pandemic. That being said, IEEE and IDK student branch has joined the celebrations by conducting a series of talks and workshops. So in our first event today, we, as a part of the Diode special interest group, of course, we have with us Dr. Prasanta Kumar Ghosh from IISc Bangalore, who will be enlightening us on the subject of Dysarthric Speech Processing. Dr. Prasanta Kumar Ghosh received his PhD in electrical engineering from the University of Southern California, Los Angeles in 2011. His research interests include human-centered signal processing, speech production, and its relation to speech perception. He heads the Spire Lab in IISc Bangalore, which conducts extensive research in fundamental signal processing and statistical machine learning with applications in education and healthcare. So without further ado, let me hand over the stage to Dr. Prasanta Kumar Ghosh. Thank you.
Sure, thanks Shreyas. Let me just share my screen and tell me you can see my screen or not.
Yes, sir, the screen is visible. No.
How about now, full screen?
Yes, sir.
Okay, perfect. So first of all, thanks for the invitation to give this, to share whatever we are doing in the space of Dysarthric speech processing. And welcome all of you. Good evening. What I'm going to do in next hour plus is to, introduce the problem that exist with a lot of opportunities for both research and developments in the area of Dysarthric speech processing, and also we'll highlight some of the key challenges and what kind of small, if I may call it, progress that we have made at our group here at IISc. So that will be the kind of overview. Before I move on, as you all know probably that at IISc in the Department of Electrical Engineering, we have this fantastic in this fantastic campus in the department. We have the Spire Lab, which I lead, and we are doing a lot of activities, including in the space of healthcare. So I'd like to just spend a couple of minutes to talk about the lab. So here is the lab webpage. Typically, all kinds of activities that we do are put up here. And this is a quick view of the lab members. That was before COVID time, a year and a half back, after which we couldn't all meet together. And here's a summary of the kind of research that we do at Spire Lab. It's primarily human-centered signal processing, and it has multiple angles. So we certainly do work with speech in a variety of conditions, and it starts from basic fundamental question in speech, primarily from speech production, to signal processing, as well as modeling for recognition and synthesis, as well as audiovisual speech synthesis, and among others, one of the important part is on speech pathology, which the topic is very much related today. And we try to also develop applications and initial prototype, which all this research can go through and see some hope of being used. And if you have any question or interest, concern, you can always please drop an email to thisparalab.ee@iisc.ac.in. With that, let me move directly to the topic. So here is a quick content overview. Essentially, we'll have three parts in this entire talk. First, we'll talk about what is Dysarthric speech, right? Including what is Dysarthria, what are some of the specific diseases that we work and we'll talk about in detail. What are the kind of speech characteristics do they have? Then I'll talk about an overview of Dysarthric speech processing that I call DISP, not DSP, but DYSP. And then at the end, I'll talk about some of the research direction that we have taken in DISP in collaboration with NIMHANS at Bangalore. And we'll share some of the experimental results and some of the insights out of those experiments. So let me begin with this video that may give you some idea about what is dysarthria. But before I play the video, I'd like to tell you this video is going to show the complexity and nuances that are involved when somebody is speaking, which appears to be seamless and very easy. It's not really so, as many of you may know. Learning to speak takes a lot more than learning to hear for a kid. So they take nearly 4 or 5 years to learn to speak very clearly. Now that boils down to the complexity in the training process and the process using which the system. So what I'm going to show here is are a set of muscles that are involved while somebody is speaking. So while that goes, I'd like to also tell you that there are nearly 100 muscles that play a role in speech production. And they all work in certain harmony, all by the brain, the nerves that connect them from the brain, right? And that in turn causes the acoustic signal to come out with the right kind of modulation. So above them, but there are some 4 examples that you see on the screen for the tongue muscles. That is genioglossus, hyoglossus, and so on and so forth. And all of these are controlled by the primary motor cortex. And we must remember that speech production is a motor task, right? Because it's nothing but the movement of these articulators that create different shapes of this mouth, and then that results in different kinds of sounds to come. So in this entire pipeline of speech production, starting from brain controlling these muscles, muscle in turn controlling the articulators, and then lung pumping the air, and that comes out. Anything goes wrong, it will impact the produced speech. In particular, if something goes wrong because of neurological reason, that is either brain or brain to muscles, that part, then that cause weakening of these muscles. They can't really act to the extent possible, and that is when we call the condition as dysarthria. I hope now it's clear what is dysarthria. So this is taken from the ASHA website directly. It is nothing but a speech disorder caused by muscle weakness, and it can be hard for any individual to talk when they are having dysarthria. And in fact, if somebody has dysarthria, you'll find it very difficult to understand their speech. So I'll now try to play 2 clips of dysarthric speech, and tell me if you can't hear them, Shrikant or Shreyas. So you can see that this is a particular person trying to speak in certain language. I don't remember the language, but the clarity is completely gone because the muscles are very weak, can't move the articulators that well. Another example. No. You see that kind of garbled speech, right? So and various conditions will cause this dysarthria. I'll just talk about in a few minutes. And the nature of the distortion, if I may call it, or the changes in the speech, as you saw, they're different because these 2 are samples from 2 different diseases that caused muscle. Yeah, so if somebody has dysarthria, what are the signs or symptoms? First, they will have slurred or mumbled speech. That will be very difficult for somebody to understand. They'll typically speak slow, and sometimes depending on the disease, they'll also speak fast. And their voice will not be loud; it will be soft. It will be difficult for them to move tongue, lips, jaw. outside the speaking, right? For example, for even eating food or any other task that involves tongue, the movements of the tongue, lips, and jaws, because those muscles are weak. And then, of course, the voice itself will change, because the muscles, of course, causes this part of the vocal tract to not articulate or not move that that well to bring speech with clarity. But at the same time, right, the voice box that is controlled by some other muscles, right, in the larynx, that also gets affected. So your voicing also gets impacted the way when you speak, and you can feel like, people are speaking through their nose, because there's a lot of nasalization because of the velum, that is the muscles that control velum to lift up and block the air leaking through the nose, won't be able to do that job anymore, or will be doing it not that well. So your voice become nasalized. So overall, you'll see this kind of changes in the voice. And there are a large number of conditions or diseases that causes dysarthria, right? Starting from a stroke or a brain injury, tumors in some in the brain, Parkinson's disease, amyotrophic lateral sclerosis, Huntington disease, multiple sclerosis, and so on and so forth, right? There are a whole lot of. So essentially, all of these, in some way or the other, is going to impact or affect the neurological part involved in speech production. In fact, because this is speech is a motor action, you'll see, we'll talk about it. It will not be just speech. Any other motor action will also be impacted for the same reason. We'll see that soon. So among all these, diseases that causes dysarthria, what I'm going to do in this presentation is that I'm going to talk about Parkinson's disease and amyotrophic lateral sclerosis. We often call them Parkinson's disease PD and the amyotrophic lateral sclerosis ALS. Now, why these two are not the others? Because we have been working with these two conditions quite extensively over past few years, and other conditions also, of course, have impact on these motor functions and speech. But for this talk, we'll be sticking to this only two. So let me now tell you what is ALS. Right? It is also called this motor neuron disease, or Lou Gehrig disease. Lou Gehrig was one of the American football player who was first diagnosed with this disease, and that's the name for this disease. The ALS came also along with this. This is a motor neuron disorder. What happens essentially is the following. So from the brain to all the motor parts, the muscles that control your motor actions, there are neural pathways, right, that connects the brain to those muscles, through which brain gives signals or command for the movement of those corresponding organs through those muscles. So what happens, this pathway, the neurons on this pathway, they die, they start dying for whatever reason. There are a large number of reasons, which many of those are not clear yet. And once they start dying, the signal from the brain doesn't reach those muscles. Very simply, it's like electrical circuit. So once they start dying, the connection gets lost and your muscle cannot function anymore. So they become weak. And that manifests into the corresponding behavioral changes. So essentially, you lose control on your muscles. That's what is ALS. But your rest of the cognitive part, everything remains, language, everything remains same. But just that all the muscles, slowly you will lose control on. Again, ALS specific symptoms, apart from just dysarthria, which is for speech, you will, of course, have muscle stiffness, a hard time in holding things because your muscles are weak, muscle cramps, even you can have a swallowing problem. In fact, many of these ALS patients that I have personally recorded many times, they die typically in few years. They die because of, they get choked. So essentially, they can't even swallow their own saliva. And that causes them to die, because that saliva goes to the windpipe. And of course, there will be speech. So now what I'm going to do is I'm going to play 3 recordings from ALS people with varying severity level. So you'll see that one is not that much severe, another is medium, another is very severe. So let me just play them. Can one of you confirm you can hear this?
Yes, sir, we can hear it.
Audible.
I'll play the next one. Okay, so you can see that from left to right, essentially they are based on the different severity level and increasing severity level. So I'm sure you have a question that different severity here. I'll come to that. Sorry. Now let's move to the Parkinson's disease, PD. Now what happens in the case of ALS is sort of complementary to what happens in Parkinson's disease. So it's called progressive brain disorder. So it's not that the pathway, the channel from the brain to the muscle, they die. Rather, it's the damage in the brain. So essentially, some nerve cells, they get damaged or they die, particularly those neurons which produce dopamine. And if there's a reduced dopamine in the brain, then they result in the muscle movement. So essentially, you can think of the controlling unit is damaged here, which can actually give command to the muscle. In the ALS case, controlling unit was all right, but the channel, the wire that connects, that sort of tear up, right? So what are the symptoms in the case of PD? Again, similar ones: tremor, stiffness, slowness in movement, difficulty in swallowing, and all of that, right? Speech swallowing. But the reason that the muscle become weak in this case is fundamentally different. You can see that, and that's why they will get reflected also in speech. And again, the similar kind of severity level I'm going to play now. So what you see here is that typically, unlike ALS, these people speak faster, but a lot of sort of not controlled well. But in the other case, they speak but struggle to speak very slowly, dragged speech and so on. Right? That's the fundamental difference. Sorry. Let's now talk about incidence rate of disease. ALS worldwide, which is not a very, as per the numbers, which are not a very severe disease, but these numbers are, the latest one is 2016. But the disease is actually, I'll say progressing, very rapidly. So a lot of such people that you'll hear with such disease. And for PD, it is, it's a good number that people are affected. About 7 to 10 million people are affected worldwide with PD. And how so that we can think of whatever solution we come up with will be useful for them. So for ALS, majority of them, another 50% of them die in 3 plus years, I'd say. 20% remaining out of remaining, people, 20% die 5 or more years, and very less number of people die 10 or more years, and remaining people will actually live longer. But for the case of PD, the expectancy level has increased. The number of years a person can live with PD has increased from over this last, I'd say 50 years, from 9 plus years to 14 plus years. That is primarily because of several treatment that has come up, therapies. But ALS is more devastating, and not like PD. Once ALS starts, it's bound to progress, and there's no way to stop it, even without therapy. Even with therapy. So how do you detect even that somebody has ALS or PD? Unfortunately, there is no specific test like a blood test or some other test that you can do to confirm. What happens typically is that you start having the symptoms and then go to a doctor. Luckily, if you end up with a neurological department or the doctor, neurologist, your luck is better than regular doctor, because the regular doctor will treat for other symptoms. They will not even think about this. And my experience so far with the doctors at NIMHANS is that, many times patients come to them very late, and that's because they might have gone to their local doctors. I mean, at NIMHANS, as you know, all over India people come there. So many times this is what I hear, that the patient has some speech problem, so they go to some local, they think that there's a problem with their teeth. So they go to the local dentist, and the dentist says, yeah, your teeth has a problem, so let's remove some teeth. It doesn't get solved, they remove more teeth. So actually, when they come, most of the time, they don't have any teeth. And when they are asked, they say that the local doctor said to remove all of them because he has a speech problem. Unfortunately, that doesn't help them. In fact, that is even that they lose those. So that's the way to. So what they do is they'll do some history check and then some neurological examination, and then they can predict. And then, unfortunately, there is no cure for either of them. Just to manage, but not to cure them. You can't cure. And as you may know, there are a lot of funding and effort that is happening for such cure of such diseases. I wanted to also tell you that there is a great deal of awareness that's happening now with this disease, because they are really increasing in number recent days, particularly for this lifestyle of people. It's we are working all with a lot of stress. And it was unlike our previous generations or even before that, right? So there are a large number of initiatives are being taken to help these people who can't even now move their muscles, move their organs, move any part of their body, to help them draw, to help them move, to help read, write, whatever they want to do in their life, being immobile. And of course, the right bottom one that Stephen Hawking, he was one such who lived long and could actually use the brain-computer interface to communicate his ideas. So, and I want to just show you this as well. All right, you may be knowing this, but I came across this very recently when this closing ceremony of the Paralympics was happening. If you watch that, you'll see that the final music that was played was produced by Pone. He's one of the composer from France, and he's paralyzed with ALS for several years now, but he can use his use his eyes to compose music. I must tell you something that I learned from the doctors about this disease, in particular ALS. It's so amazing that your eyes, which require movement, right? That requires muscle. Again, it's a motor action. The lungs, the diaphragm that helps you to breathe, right? That is also some kind of movement. These are things that continues to work as it is till the death. So these are things that can be used to help them. And in fact, people have been trying to do that. So the movement of the eye has been used in a big way for many of these patients to help them, develop technologies to help them. And in this case, Pune has really mastered that art. And if you just search with his name, you'll find that he has a setup in he's lying down all the time, can't move at all, but with his eyes, he can compose music on a screen that is in front of him. And that's amazing that's possible today. So now, with all of that as a background, I hope you're sort of excited to see what's going to happen in this space, because it requires a lot of engineers like us, apart from neurologists, to think of solutions that can help people, life of these people. So now let me come back to the question of severity, right? How we'll call severity for each of these diseases. There are two main, or the only one that is available to give a score on a scale. One is called the ALSFRS, right? And MDS-UPDRS. So for the ALS, the scale is called ALSFRS-R, which is the revised version that has come up recently, and the MDS-UPDRS. I'm going to talk about each of them now. So the ALSFRS is the ALS functional rating scale, and it was originally proposed, and there's a paper that you see in 1999. So it has a large number of aspects that it examines of a person with ALS. Of course, it starts with speech, right? So you can think of the scores being 0 to 4, 0 being loss of speech, and 4 being normal, right? There will be somewhere there. And there will be many others apart from speech. Salivation, swallowing, handwriting, cutting food, blah, blah, blah. There are 12 of those. And essentially, when somebody has to give a severity level, it has to be given for each of these. So when you work with speech, the doctors are asked to give a severity level for speech only, right? And it is not that all patients with ALS will have difficulty in all of them at the same time. So in the beginning, it's very difficult to know which one will come first. It depends whether it is which kind of motor neurons are getting died. Depending on that, different parts of the body will get affected. On the other hand, the MDS UPDRS is coming from the Movement Disorder Society. This is the revision of the Unified Parkinson's Disease Rating Scale, right? UPDRS. So even here, these are all publicly available, so somebody can use it. But I think you have to use their get their permission to use this. So there are again a large number of parameters that they examine to tell severity. And they are primarily broken into a major 4 parts. So part 1 is on non-motor aspect of experience in daily living, right? This starts from cognitive impairment, hallucination, depressing mood, all of that, which is nothing to do with speech or motor action. But the next one, which is on the motor aspect of experience in daily living, as you see, there is speech, saliva, drooling, chewing, swallowing, all of that, right? Which is all of these you see in this list are require motor actions. In fact, within each of these, I didn't show for the previous 2. Within each of these, there are, again, the score or scale. And here's the opposite, right? So 0 is normal and 4 is severe. So that means 4 means that speech can't be understood. So for each of these, the neurologist or pathologist, they give the score, which is 0 to 4 in each of these cases, and overall score will be accordingly determined. Similarly, motor examinations, again, speech comes. And finally, again, similar kind of 0 to 4 scoring. And finally, motor complications. So just to give you a sense that both ALSFRS and MDS UPDRS, although composed of a large number of parameters to monitor and assess the severity of the person, speech is one of the main components there. And when I mention about the severity of speech, they are actually referring to the scale here between 0 to 4. So next question comes, of course, great, we have now defined what is severity, what kind of scale we'll use for severity. The next question is, if somebody comes for examination, clinical examination with such condition, and to tell them that what kind of speech quality or severity you have, what do you ask them to speak? That's only when you listen, you can only tell them, right? And the question is, they can speak something naturally. That's one way to do. Will you do that? Will you try to figure out some specific aspect in speech that we have to probe and get those scores? Indeed, that's true. So this is primarily tied to the perceptual features. So what happens is, for different kinds of dysarthria, as you see on the first column, it starts from spastic, flaccid, mixed, and all of that, right? They are defined based on what aspect of your speech production get impacted. For example, if you have articulation inaccuracy or vowel distortion or prosodic abnormalities or breathing voice, see, all of these are coming from different parts of this organ that helps you to speak. For example, if you have too much damage in your muscles in the voice box, then you'll have vowel distortion, or prosodic abnormalities, because you'll have pitch that it gets not well controlled. Even your voicing will have a lot of breathiness, right? So if you take an example, for example, the last but one, right, hyperkinetic. So you see the tick marker given for the articulation accuracy and the prosodic abnormalities, where in this particular condition of dysarthria, people have difficulty, or the patient with dysarthria will have difficulty in controlling the, I can say, on-off of their pitch, the voicing and unvoicing. That becomes very difficult if you have that. I'll show some examples, you'll see soon. So based on, and here is a more detailed description on, for each of these flaccid, spastic type, what parts of the motor neuron gets damaged, was the lower part, upper part, and many more. If you're interested, you are welcome to look at this reference. This is really a good resource for understanding all of that. But based on these, perceptual attributes, what people have come up with, the clinicians or the pathologists have come up with 3 types of speech tasks. The first one is called respiratory phonatory coordination, which is where they ask patients to have sustained phonation, a sustained voicing. For example, you speak on saying ah kind of thing, right? For as long as you want, because then you can understand how much, if the muscle that control this holding of the breath, right, that will help you to speak longer, sustain the vowel longer. If they are weak, they'll quickly die out like ah, right? Or even the pitch, how much they can sustain. That will help them to assess the muscle of the vocal cord, right? So on and so forth. Similarly, the next one is diadochokinesis, I just mentioned a while ago. So these are speech-like movement during rapid, single and double and multisyllabic utterances. For example, it will be like pa pa pa, right? So you say pa 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 as fast as you can. This requires a lot of coordination of the brain to muscles that you have to put on and off, right? Apa 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 like that. So you have to have on and off of your voicing. Ah is a voice sound, pa is not voice sound. So that will cause it to cause the system to really be tested. Then speech characteristics, there are a large variation even within the speech. So it can start from single word, sentence, paragraph, conversation, or spontaneous speech. And all these cater to, or rather target to, find out the voice quality, either it's voice quality or nasality or articulatory precision and intelligibility, all of that. So when you come to the natural speech, either through word, sentence, or conversation or spontaneous speech, they examine all of these aspects. And based on all of these, they take a call on those severity levels. And that's how they ask the patient to do each of these tasks and then hear and then give a score. So just to give an example, how the waveform looks, you already heard quite a few, but I just wanted to show you here how the diadochokinesis, example, that pa pa pa. So here are 3 cases with 3 different patients, one from ALS, one from PD, another from healthy control. By control, it means healthy subjects. So all of them are asked to speak pa 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 as fast and as clearly they can. So in the case of ALS, as you heard, right, they are speaking like that. They're speaking. So even in 1 second, they could only speak 1 time. In PD, it is not as fast as a healthy person, but it is lower than that. And in a healthy person, it is much faster. I'll just play all of them to see if you can hear them well. You can see. And this is a healthy person. So you got the picture, right? So this clearly shows that these people have challenges. So that concludes the first part of the presentation. Now let's move. Any question, by the way, at this point from any of you? Because I don't see any of you. Okay, perfect. All right, I'll continue if there is no question. Let me move to the second part, which is on the overview of the Dysarthric speech processing. So we'll see what kind of research question that people are engaged today to address this kind of speech. So here is a quick overview of that, right? And there are a lot of directions of research and analysis and examination that are happening. I'll just not go through each of those because each of them by itself can be an hour-long talk. There's so much work has been done in each of those. So I'll start with I'll just give you a brief and 1 slide summary with some references so that if you're interested, you can pick those up. So the quality of life is something that people have been working constantly. What is quality of life? So QOL is a way to quantify how severe is or how impactful is their current condition, a patient with dysarthria, their current condition on their life. Meaning, for example, there's some of the tragic situations that I hear that the patient, lying, there has to be a caretaker, by the way, otherwise it's very difficult for them to maintain their life. A mosquito bites them, they can't either hit it with their hand, nor they can call somebody because they can't speak even. So a solution even to help them in this way is just pathetic quality of life, right? So people have been trying to give a measure on that how do you tell that this is their quality of life? And people have tried to use speech to see what aspect of speech, parameters of speech, actually directly correlate to their quality. There is another part called augmentative and alternative communication, AAC. So as I just showed you, with the eye movement and blinking, you can do a lot of stuff. So these are alternative communication ways. And people have been developing technologies, doing research on that front as well. Automatic Dysarthric speech recognition, right? There are large groups, from well-known firms. They are working on developing speech recognition solutions for this kind of speech. These are not natural speech. We have enough challenge with natural speech recognition, and this will add on top of it even more. Coming to the acoustic analysis of Dysarthric speech, well, there are large number of questions which we need to understand and find answer for, starting from how they are, let's say, basic question like format changes, vowel triangle changes, voicing characteristics, how does it change, how their entire acoustic space changes, which sound they can produce well, which sound they cannot. There are varieties of such questions that people are addressing, right? And then the next one is articulatory kinetics analysis, right? Because muscles are the ones which are weak, they directly in turn impact the articulatory motion. So people are interested to examine the motion of the articulators directly while they are speaking. So for example, you see, I'll tell you one example, they find it very difficult to move their tongue independently because the muscles that I showed, the names in the very first slide, they control their tongue independently, right? When you say ta, right? You see that your tongue, instead of lying on the jaw, it goes up and hit the palate, right? Ta. But for these people, they can't move their tongue independently. So they have to move their entire jaw. So they say ta, like that. I don't know whether you could see me doing it. And I mean, we have seen that. I have seen that face to face. It's just so difficult for them to move their tongue independently. So doing articulatory analysis, if you can access, will directly tell you what kind of problem they have in that space and which muscles may be weak. Then, of course, the whole question of can you detect early this kind of disease, because it doesn't happen one day suddenly it starts coming, right? There'll be slowly your speech will get slurred, slowly your speech will get distorted. Can you detect that early in your life, early in this journey, and then monitor them also as they got detected? So I already told about each of these, but still just to specifically point out few key questions in each of these, right? For example, in the case of quality of life, is there any relationship between the degree of dysarthria and the quality of life, or does the time of the diagnosis anything has to do with the perception of quality of life? See, this is a very subtle question. So if at the age of 28 you are told by the doctor that you have got this deadly disease and your life will end in 3 to 4 years, imagine the quality of life will completely change, whether you could run at that point of time or not. It's just devastating. And the doctor we work with, they have to do this every day, and there are, I'll say double-digit number at least every day in the clinic where doctor has to give this verdict to them. It's like it's a death sentence. That, yeah, and the entire patient party gets devastated with that. Certainly, there is nothing else that can be. So the question is, if you don't even tell them at the time of diagnosis, will that help them to even live longer? Because they mentally get completely, devastated. And I mentioned about these AACs, right? Eye tracking, brain-computer interface, which was for Stephen Hawking's voice message banking, personalized details. There are a lot of such speech technology that, and of course, non-speech technology that can help. About speech recognition, this is the work from Google. They have been working on, low resource condition for personalized ASR for this kind of speech. And as I mentioned already about varieties of analysis that can be done on dysarthric speech, right? And some of the references they are in. So if you're interested, you're always welcome to read them. About articulatory kinematics, I told you the reason, the rationale behind. So typically, the doctors, if measurements are available, they'll find out the velocity with which they are moving, the coupling between different articulators, the acceleration or the duration of the motion, rate of motion, all of that are typically used for assessing the severity of this disease or condition under this disease. And if you can come up with a technique based on the speech or any other action, right, for early detection and monitoring, that's of great value. It particularly because there may be a lot more patients which, being unaware of this condition, of this disease, they may not be even getting treated correctly, right? So it's always good to develop such things so that it can help a lot of people to detect early and come to doctors. With that, I'll quickly complete that overview part, and then let me move on to the some of the experiments that we have carried out with this speech, and to tell you what kind of findings we have in that regard. So what I'm going to do in this part is that I've structured the experiments in a way so that it really tells the story of our finding. So for that, I'd like to tell you the following. We started this work in collaboration with NIMHANS, right? Dr. Yamini, Dr. Nalini, and Dr. Ravi Yadav. We have been doing this for now a few years, and we have started collecting speech recordings from several PD and ALS patients. So this is our recording setup, but before I tell about the setup, I'd like to just tell you the following. So with the recording that we do, we ask specific kind of questions. It could be questions starting from simply, what features in your speech can tell that this speech are different from normal speech. That can be the simplest question. Is it possible that you can even classify between ALS and PD, as you see there, right? Or what kind of features that are really useful, that can learn them in event manners, simple thing. And then we can really create really complex model with those learned features using neural network and many other deep networks. But is that really useful in practice? Because we'll be mostly doing with lab condition recording and really complex models. But you have to deploy them on some device locally without internet, because a lot of these people won't have probably internet. Even many of them are so poor, they have only feature phones sometimes. So question is, how do you develop robust and less complex models for doing a good job of detecting them, that they have this kind of speech? And to understand whether your source component, meaning the vocal cord versus the vocal tract, which part actually contributes to or provides more cues for identification of such diseases, right? All of those we'll be talking about. I hope that gives you an idea as to what are the questions we are asking. But now let me go ahead and tell you the recordings that you do. So this is the recording setup, as you see at NIMHANS. So this is a top view of the table where all the devices are placed. So from the left, there are, you see two phones, Apple and Xiaomi, and then you have the high quality Zoom recorder, you have the Motorola phone, and then the laptop. So there are total 5 recording devices. And why 5? That is because when we collect this data, if we have recordings done in each of these devices, it helps us answer quite a good number of questions. Number one, is there anything that changes from one device to another, right? Because in practice, different people will have different kind of device. Not all of them will speak in one kind of phone. So these phones are chosen depending on the price range. Some are cheap price, some are very expensive, like Apple will be very expensive, right? And of course, we have laptop and a good quality recorder, so that the good quality recorder can capture the best recording that is possible. Here are some of the snapshots of the recording that one of the experimenters was doing with the subject that you see here in front of the laptop, right? And the biggest challenge that we faced, by the way, when we started this work together was the following. We are wondering that what will ask them to speak. So for example, I talked about this task, right? They are to ask, just speak pa pa pa. That is easy to tell them, and they can try that. Or say ah or e, for instance. That's also good. But when it comes to speech, there are multiple hurdles. So if you ask them to speak something naturally or spontaneously, it is just so annoying for them, because even if you tell them to say, let's say you're some kind of outing that you have because they are anyway not going out, right? Their life is miserable. So they always fall back to their, daily problems, sad time, and start crying. It's very, very challenging to record from these people. And then, if you give them a sentence to read out, they can't, because many of them are illiterate. And even if it's in their local language. And so we thought about it a bit, and then we came up with what is called a picture description task. So where we present them some pictures, it could be funny pictures so they're engaged, not bored, and they have to speak one sentence about that picture. And that can be anything, and we don't really care what they speak, but they have to speak something what they think, right? So this picture description task is this first one. Then we have the spontaneous speech, right? We anyway ask them for 1 or 2 minutes. Again, that becomes challenging. Then DIDK, which is diadochokinesis, which is repetition of the syllable, pa 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 pataka, like that. And then finally sustained version. So those are 4 tasks we use. I can show you. I can play some examples of those, but I think you've got the picture. I think I'll play the pa pa pa. That may give you some clue. This is for ALS. Correct. Then let me play the PD. You, I think, heard this before as well, right? So, and the healthy will be quite good, right? So that, and this is one of the key experiment or key stimuli that doctors use typically. Sustained function, again, a similar type. You can feel nasalization already in it. So, and they stop. Sorry. They stop because they can't really go long. And if you look at the PD, you see there's some struggle that there. You see the difference, right? There's some clarity. Okay, so we have been working, as I said, recording this different speech stimuli over a few years, and you see this experiment that we'll talk about, and the result we have published also periodically. And you'll see that all the experiments will not have the same amount of data, because in the beginning we had less data, we could answer these questions with less number of data, and as we went ahead, we found more and more data, and the models we could build and could answer better and bigger question as we go forward. So the very first question, with the very little data that we had in 2018, we asked that, okay, what kind of features in the acoustic and articulatory space? We actually did recording of articulatory data, which I didn't talk about. It's really painful process to record anyway speech data from them, but articulatory motion data with this specialized device called electromagnetic articulograph is even more challenging. But we had some recordings from these people, so we asked, okay, if I take the ALS and healthy people, can we really use some features from this and then tell that those are the key discriminator for these 2 classes? And for this, we had rehearsed speech, spontaneous speech, and repetition of words. The first task was very simple, that my name is blah, blah, and I'm now in Bangalore. So they speak in their native language. All of them are from Kannada, right? And then the task 2 was to produce a monologue. They speak whatever they want to speak for some time, however minutes, and 2 times they have to do that. And then the last one was repeating Kannada words. So like the doctor says topi, they have to repeat topi. Karnataka, Karnataka. Right? So I'll just quickly show you some of the details of the subjects that we have. So very little in the very beginning, as I said, we have only 8 subjects healthy and 8 patients with ALS. You can see their ALSFSR scores at the bottom. So they are sort of towards kind of severe, but not 4, which is extreme severity, right? So with this, and there are some male, female, of course, balanced to the extent possible. So with this small data, we recorded the motion of their tongue tip, tongue body, tongue dorsum, lower lip, upper lip, and jaw. And here you see the amount of data per subject that we have for each of these tasks. right? So it's very little data, not much. And then we ask this question, okay, what are the features that we can use? So the first feature we looked at in the articulatory space was more than just their position and using them blindly. We computed the velocity features, and we compute the velocity norm and acceleration norm, right? So we call them as, so by the way, all these features for each of the sensors, right, that are attached to upper limb, so we typically record their movement in the mid-sagittal plane, not in the 3D, right? So it will be only X and Z. Like that, we have the measurement from all the sensors, and we compute velocity and acceleration norm for each of these sensors. And we call them velocity features, then acceleration features, then together. We also use the static features as well, and velocity and acceleration, all of those. And then we use MFCs as a standard feature of the acoustic, and we use all of them, right? So these are the kind of features we experimented with. And very simple classifier with SVM. What we do is we don't give this feature as it is, but we compute what is called suprasegmental feature, meaning you take some segment like 0.8 second and compute mean and standard deviation of these features. So this captures how much these features are changing with time. So if you can imagine if over 1 second, a healthy person will speak a lot more things than an ALS, right? So it will sort of capture the variability of those features, and that is what is fed as the suprasegmental feature. Very simple feature, simple classifier, and we get the predicted level. Let me show you some of the results, right? With these different features I just mentioned. What was interesting is that compared to MFCC, the articulated features were much more accurate. So if you look at the SVM classifier, forget about DNN, for the time being, for task 1, the velocity features was much better. So this is the F score that we got using velocity features, while it was 0.95. Similarly, you see 0.92 this task 2, and with even all the features we get 0.92. And so on an average, the features from the articulatory space, they do much better than the ALS, than the acoustics for the ALS healthy classification. And that's true for even the DNN. So it says that, the muscles directly reflect their weakness in the articulators. So of course that in turn gets captured in the MFCC, right, which will be acoustically captured, which has to be acoustically captured. But if you directly tap the articulators, which is challenging in practice, it will give you the better accuracy. With that, we asked, okay, fine, no problem. If you have to go ahead with even acoustics, MFCC based, will it matter what device you use? Does this accuracy change from device to device? I'll just show a quick glimpse of that. So here we already got few more subjects, like 50 subjects now, and we use the same classifier as SVM-DNN. As you saw last time in the view of the recording setup, we have these 5 different recording devices. So what this on the right we show is for 3 different tasks: spontaneous speech, DDK, which is called diadochokinesis task, and phonation, how the performance changes with the frame length, the segment, right? It took this 0.8 second and then shift by 0.2 seconds. So that 0.8 will vary with various chunk level over which the suprasegmental features are captured. And what you see in each row are different devices. So as you see, for example, DIDK does the best job in terms of their accuracy. So you can see that the accuracy, if you go from one device to the another, right? You go across, it changes a bit, right? Motorola to Zoom to Xiaomi to laptop to iPhone, like that, right? You see there's some changes, right? In particular, Motorola and Zoom was the best, but Motorola was little worse than Zoom. So, but it's not drastically changing, and more importantly, it's not changing much from one segment level to another segment level. So 0.8 was pretty much good. But DIDK was in general better than spontaneous and phonation in terms of providing the accuracy. So as per the task, DIDK is better. And as for the device, so, right? You can use Zoom if you have, otherwise you can use the Motorola, for example. So once I had that, okay, probably devices are not that critical. The question is, okay, let's go ahead and ask, is there cues, or are there cues which can discriminate ALS, Parkinson's, as well as healthy subjects, right? So that we can have a classifier to do all three types of classification. And now we are getting more recordings. So we said, well, let's go for a better model, not just SVM DNN. And we can also check whether better modeling actually helps to do a better job of classification. So for that, we started with the CNN-LSTM network, where we have the acoustic feature segments, right? You can give this MFC sequence, and then you run on the CNN, do max pooling and for the LSTM layers, which will finally fit to the dense layers. At the softmax, you get the classification output. But when we apply for test, what we do is we run this on multiple segments. So suppose there is an utterance, right? A sentence recorded for an image that was spoken. And then you have this chunk, multiple chunks, 0.8 second, 0.2 second shift. For each of this chunk, we run this classifier, we get some level, and do a majority voting. And then the entire utterance level decision was finally put up, because that is more accurate. And we also did, transfer learning approach, considering the fact that this kind of data is low resource anyway, right? So if you have, let's say, a lot of data of Parkinson's disease patient, but not ALS, and vice versa. If you build a network with Parkinson's disease and have little data of ALS, and then if you can adapt, right? Can that adapted network do well on the ALS classification, ALS versus healthy classification? So here you can see that we do the initialization using ALS versus healthy, and then we use the Parkinson's tool. And rest of the network, the strategy remains same. So we had then three objectives of this experiment. We said, well, does the better model, CNN-LSTM, does better job than SVM-DNN for ALS versus healthy classification? Next was transfer learning. Does it help if I have a pretend model using ALS healthy control and then use little data of Parkinson's disease and have a new model to do a Parkinson's healthy classification, and vice versa? We can do it for ALS also. And then finally, can we do a direct 3-class classification? And now, as I told you, we got a lot more data. We have 60 ALS, 60 PD, and 60 healthy control. Gender balance, you can only go to this level when you have a lot more data, because the patients we have no control on what is their gender, right? We have to really wait for sufficient number of patients to come so that we can have this balanced gender, right? And you can see the amount of data and everything that kept on building up. So, and we systematically did the experiment with 5-fold cross-validation, each fold containing balanced number of patients, classes, right? CNN-LSTM with the MFCC computed. So these are all details so that we make sure, we are not really doing anything wrong. When our result comes out, we have the right interpretation of those results. So now I'll talk about the results for each of those questions that we had. First question, is a better model CNN-LSTM doing better than SVM-DNN? And here are the results. As you can see, yes, it is doing better in all the tasks. And as you can see, DIDK does the best. Phonation does the best with the CNN-LSTM. Spontaneous does the best with CNN-LSTM. Because what we have found is the spontaneous, when somebody is speaking spontaneously, it captures their natural pauses. So they're not forced to speak about something. So they think and speak. And that style of speaking, the pauses particularly, they actually get captured and gives the highest accuracy. But if you look at the DNN-based model, the DIDK does better. And it's not that DIDK is very much worse than spontaneous, because again, DIDK also, right? As I told you, the coordination is very tough to achieve. But phonation is not that much. You just get 89% because it will just speak and probably there is not much articulation variation-wise information present there. Then we said, well, let us try the transfer learning approach and see whether it indeed benefits. I'm going to now explain you one of the graphs so that it helps you to understand. So let's say we take this bottom right graph, right? This is for the task of phonation, like sustain kind of thing. What blue curve shows is that you use, let's say, 100% of the data, meaning you use the entire data for the PD versus healthy classification, right? So whatever data you had, you use the entire data for training. Of course, you did 5-fold cross-validation and everything. And then the network is randomly initialized. And you get, let's say, 75% accuracy for Parkinson's, right? As I told you, for ALS, it was 89%. So here is Parkinson's is 70%, near 70%. Now we said, well, that's fine. Can we do the following. You can use this 100% of the data, but don't train a network with random initialization. Rather, train the network which has been already trained with ALS data. And then start with this 100% of the data to retrain. And then you get a benefit. Because I think the network already trained, started from a better point, not random point. And that becomes very much prominent when you use on, suppose you assume that you have only 10% of the data because of the low resource condition. This is simulated low resource condition. So you start with only this 10% data. Of course, it will be very poor because random initialization, not much data will be poor. But when you have, the ALS pre-trained model, you get much better accuracy. I hope that clear. And that happens almost for all the tasks and both the classification. Here is the 3 class. We also did directly 3 class. You can see that here the IDK does better. In fact, we use this 3 class to get the 2 class accuracy, right? Where you take the corresponding output of those classes and compute 2 class accuracy. Then what we did, we also did fine tuning FT, meaning we had this 3 class with a lot of data, and then we fine tune it with little data of Parkinson, or little data of ALS. Actually, that does really a great job on the ALS subjects. That has really get the best performance of 98%. Similarly for PD, that's the highest. So far so good. So we have got now, better model. We have got MFCC features fed in all acoustics, no articulation because it's difficult to get articulated data. And then we got good numbers with this complex model for both the task of ALS versus HC and PD. Sorry for the typo, PD versus HC. Now the question is it the best feature? Is MFCC the best feature? Should we learn these features? These are obvious questions that people have asked in speech recognition and many other tasks, right? So we said, well, instead of just putting MFCC as input, let's put raw waveform and put a representative learning block with framing and learning CNN filters with batch normalization and max split. Rest of everything remains same, right? And then let us see what kind of features or filters do we learn. Again, there's the same data as we just saw, and we now use all the tasks, 4 tasks, not 3. And again, thorough experimental examination so that they're systematically done, both for the proposed and the baseline. So baseline is nothing but without representative learning, the one we just explained, right? We use the MFCC as the input. That's the baseline. And the proposed is raw waveform, and you learn the features. And here, what I'm going to do here is I'm going to now present result for each of these classification tasks, and I'm going to compare the MFCC based results and the raw speech based results. So if you look at the raw speech based results, you see whenever it's higher, significantly higher than the MFCC, we just color code it using blue. And if you see for this ALS and healthy control classification, we did a task-specific model. For each task, we develop separate model. And there is pooled model where we take all the tasks and build one common model and test on the separate task. So you can see that for except for spontaneous, there is improvement in the. Of course, you see no improvement and no significant changes in the spontaneous case with the raw speech. For Parkinson's versus healthy control, you can see again majority of the cases it improves. For ALS versus Parkinson's, you see that again in half of the cases it improves, right? In both the task-specific and pooled models. So then you say, well, it looks like there are some cases where it's improving. So let us look at the filters. How do they look? Is it like male filter bank? Answer is no. It's not male filter bank. It turns out that most of these filters are all well below 800 to 1000 hertz. So in fact, for ALS versus PD classifier, that is all below 800 hertz. For PD versus healthy control, they are below 500 hertz. All the center frequencies. As you can see, these plots, probably you all know, we rank order all the filters based on their centroid of the spectrum, and so that it shows that how the center frequency of the filters are changing. And for ALS versus healthy, all the center frequency of the filters, learned filters, are below 400 hertz. So this is something that really banks all up to 8 kilohertz, and that's why it's doing better job with learned features than MFCC as well. What is that is causing such thing? And when the frequencies below 500 hertz comes in picture and becomes useful, we are thoughtful and thinking that probably there is something to do with the vocal features, vocal source features, not the vocal tract features. And that was our next set of questions that we'll be asking. But before we go to those questions, we asked, well, great that you have come up with MFCC and learned features which are doing great with with complex models and clean condition recording. How will they do if there is noise in it, right? How will they do if the classifiers that you have built are not that complex and can't be used in a resource constant condition, maybe simple phone that cannot even run that much, not over cloud or anything like that, right? And this is a question we focus on in this paper this year, ICAST. So we said, well, how about pitch? That was our suspect, right? That if filters that you learn are all below 500, probably pitch has something to, some role to play. So why don't we examine the role of pitch as a feature? It's just a single dimensional feature. So the model won't be complex because it's a single dimensional feature, unlike MFCC or many serial learned filters. So we went ahead and used swipe and pfec as pitch extraction. And I will just show you an example that will be much more clear. So here is a clean recording and the 0 dB recording. You see the pitch contour estimated using swipe and the MFCCs. You can see MFCCs changes drastically, but pitch does not. And we thought that if pitch by itself has a good discriminating power, probably will not lose the performance using pitch, but MFCC will certainly lose, right? So if your model is trained in a clean condition and you deploy it in a noisy condition. So this is a white noise at 0 dB. So we went ahead, we said, well, let's use the same classifier. Input could be MFCC or pitch, right? We'll use the chunking, CNN STM, majority voting, and all of that. So we said, well, let's try out different complexity to control the complexity of the classifier. One is memory complexity, number of parameters, and the runtime complexity, number of flops, right? And we control the number of parameters in the CNN STM to create 3 kinds of complex networks. One is low complexity, medium, and high. Just to give you an idea, what does it mean? So think of this for the pitch, right? Here is for the high complexity network, which has nearly 55,000 parameters, to match with the 55,000 approximately for MFCC as well, for both pitch. But pitch has only single dimensional input. MFCC has multiple dimensions. But we want to keep the model complexity same to compare the performance. So you can see the details with the the CNN layers, the max pooling layer, the LSTM layers, and all the way to the dense layer, right? So we create these networks and feed these two with these 3 conditions, and we wanted to see how the performance changes. Again, systematic step. Here we use Gaussian noise, additive Gaussian noise at 4 different decimals. And we have 2 conditions. One is match and mismatch, meaning in one case, we train with the noise data so that the testing condition is aware of the noise and the SNR. But in the mismatch, the training data is only used for training. The training data is only clean, right? Testing is done on the noisy case. Here are the results. It has a lot of findings. First of all, we found that swipe performs better than pfec. So if you see the green and the red, you see that most of the time, the blue or the violet and the green. I'm so sorry. You can see that most of the time the swipe, which is the violet, is better than the green, right? But you can see that MFCC does many times better, right? MFCC is the last one at different noisy conditions because this is in matched case. You can see that for PD versus HC also. But if you look at carefully, that the MFCC performance is almost same as the pitch performance here. Here it's different significantly and so on and so forth. But these are all in matched condition again, right? Then you say, well, let's go for mismatch condition and see what happens. And we only went at this with only this swipe-based pitch. Now we see a drastic drop in MFCC because MFCC was trained with clean and tested on noisy. It will certainly fail, but pitch does not, even at 0 dB. You can see that, right? So then it was, and it's giving accuracy more than 80%. In fact, in the previous case, accuracies were near 90%. So pitch as a single feature captures something that MFCC, which captures vocal tract as well as speech together, gives almost equivalent. So it indicates that probably the way these diseases impact the muscles could be, part of it actually is there that is contributing to the pitch or the oscillation on the vocal tract, and that is when captured does very well. Then we said, well, then let us go back and ask this question specifically. Can you compare how much the source and how much the vocal tract contribute to this classification? What I did is very simple. We tried to create features where in one there is no voicing information, vocal cord information. In another, there is no filtered information. So for the case where there is no filtered information, we said we'll use pitch. But where we want to avoid the vocal cord information, we did some special strategy here. I'll just talk about. But this is, as you see, we are doing it for only PD versus HC task. And as you see, the summary of the subjects that we have used, a pretty much subset of what we have used before. And so coming to the features, right? For source features, we are using the pitch. For vocal tract features, we use something called voice removed MFCC. I'll talk about that in a minute. And we, of course, combine them, which is, combine in the sense we explicitly combine and also directly use MFCC, which captures both source and filter. So how do we remove voicing? Essentially, we use the word analyzer, where we break down the speech into F0, spectral component, and aperiodicity, and then we replace the entire F0, which is speech, by 0, and make aperiodicity to be 1, so that there is no voicing at all, right? And then synthesize back the speech. So it will be like a whispered kind of speech, and then you compute an MFCC of that, and that's called the VRMFCC, voice removal MFCC. Right? So these are various dimensions and the toolkit that we use for MFCC and pitch, and the temporal settings that every 10 milliseconds we compute this. We experiment with varieties of combination of these features, right? Individually, like pitch or voice removal MFCC or MFCC, or they're all kind of combinations. And again, classifier remains same, CNF STM. So as you can see, the number of parameters, we just want to make sure that the number of parameters are same, so that we are not unnecessarily creating complex network for complex features and simpler network for simpler feature, right? Feature, irrespective of feature, the network is equally complex, so that you can compare the features. Again, experimental details to make sure. Here we have added a few more noises: high frequency channel noise, pink noise, and babble noise in 4 SNR conditions, and in both matched and mismatched. So the first question was, is pitch doing any better than VRMFCC? Because that's what will give the answer. And we have a sort of a mixed result. What we found was that when it is spontaneous speech, pitch does better than VRMFCC. These are significant. By the way, when I put a green, blue, it means they are significantly different, but the other cases they are not. But in the image task, the filter does better. But of course, overall pitch does better. So pitch as a single feature does really well in spontaneous. That's what we have found. And again, it goes back to the hypothesis that when people are speaking naturally, they give their natural way of pause and voice to unvoiced transitions, and that are very, very characteristics of the Parkinson's disease. Then we said, well, let us now compute each pitch, MFCC, VRMFCC, and together, right? And what we did is we did all kinds of comparison. So we said, well, does F0 plus VRMFCC does better than, do better than individually? Does these two together does better than MFCC, right? All of those questions. So here, whenever there is a star marks, it means that it is doing better than pitch. When there is a triangle, it is doing better than MFCC, VRMFCC. And whenever there is a hash, it means that the MFCC, this jointly is doing better than MFCC. Right? So, for example, the highest performance again was obtained using pitch and VRMFCC at 90%, and the accuracy was 90%, right? And in fact, only pitch was 88%. So you can imagine the pitch actually carry a lot of information about these classes. Same kind of features, but now this time we also fuse with F0 and MFCC. So it did various kinds of features. I think the key message is clear to you that the best reference we got here was pitch as well as MFCC. So pitch being explicitly present helped the classifier learn this voicing pattern in a spontaneous speech, and that's really a great cue. We have repeated this experiment in train and test mismatch and match condition. Here is a match condition, and again, a pitch turned out to be a very clear, well-performing feature in the mismatch case, in particular with high noise condition. And so we call F0 to be noise robust as well as SNR robust feature for this classification task. So with all of that work that we have done, we have built an application which you'll find in Google Play even. We are working on it to improve, called Neuro Companion, where you can go and speak. And we have a model, one of these models that we have now deployed, where you can speak and the model will evaluate and give you a score between 0 to 1 to show where you stand in terms of healthy to ALS or healthy to Parkinson's disease. And this is a application where there's some gamification. You can play some games and try out. You're welcome to use and give feedback, and be happy to hear from you. So with that, I'll stop with these three main conclusions. As you saw, the acoustic articulatory characteristics in Dysarthric speech requires to be understood and analyzed in great detail to help develop technologies for monitoring and many others, right? Detection. And you have to build technologies based on those so that we can help these people. And this is really a need of the hour. In fact, I was talking to one of the ALS association in India. They say that we really need to develop these AAC solutions for these people, because many of them are paralyzed. They can think they can do everything, but they can think to do everything, but can't do anything. Okay, so it's really need of the hour. And there are hundreds of them. It may sound very minimal, but it's just devastating for those people who are going through it. And for this, you have to not work alone, right? You have to work with neurologists, pathologists, the people who are into the society, societal job, NGOs, really to work together to find out the real problem with these patients and develop solutions for them. So with that, I'd like to acknowledge all the students and the collaborators, and of course DST. We have been having projects funding from them, which helped us to do all of this research. And thank you all for being patient and listening to the lecture here, or whatever I talked about, our research. So I'll stop here and wait for any questions if you may have. Thank you.
Thank you, sir. That was very informative. And now we have few questions from our audience. Am I audible, sir?
Yes, please go ahead.
Yeah, like the first, we'll start with the basic question. Like one of our audience have asked, like, can we use traditional speech features like LPC or like vocal tract modeling to characterize dysarthric speech?
Yeah, we have experimented with all of those LPC but as you probably know, the challenges with LPC is that they are not very well known. PLP may be better, right? But the LPC, the challenge is that a little change in those coefficients causes a great deal of change in the spectrum. So even two similar spectrum can have different. So LSF maybe, or LSP may be a better, line spectral pair may be a better feature. But we have found LCC doing better than any of those.
Okay. Yes, sir. Now we'll move on to the next question. Like, this is a practical aspect. Like, is there any open source data set for dysarthric speech?
Yes, there is. It's called the Torgo dataset, TORGO. It's not Indian dataset. It's from a Canadian lab. This is by Professor Rudzig. Okay, so he has been working on this kind of work also for some time. So if you're interested, you can also ping or search for that dataset.
Okay, I think Shashank has noted it down. And moving on, we have another question, like does language or difference in languages impact the difficulty in learning these features like MFCC or pitch, like for dysarthric speech?
Yeah, no, I mean, see, that's a good question. Considering this problem of classification of, these two classes, right, dysarthria or healthy, we haven't found language-specific pattern in particular, because we have asked them to speak whatever they wish or target like DIDK or a phonation, right? They're very specific tasks. So we haven't found any such. So these are all language agnostic, and we didn't find any language-specific pattern in the result also. But you're right. This is something that we're trying now, is to see, if there is anything to do with language in terms of their communicability. So think of this. So suppose I play one of these recording, right? If it's severe, you'll have a difficulty in understanding that. But it may change from language to language, because in some language, there are some words which, although may be deformed, but you may still recognize it, unlike another language. So we are doing that study to see whether there is any language-specific pattern in terms of recognizing them by human or also by machine.
Okay, sir. Okay, now the next question is it's a bit interesting. Would using different format locations as features along with pitch information improve the accuracy of the classification?
Good question. We have used formats as well, right? But the challenge with that is that, and by the way, so I'll tell you the final answer. Again, MFCC does better than that. We have used formats, but the challenge is that we have to be very careful in terms of whatever algorithm we use for the formats, right? And then if there are errors in the format estimates, again, things go a little tricky. So although we can use that, you can do experiments, and we have done that. But again, the best result that is showed with pitch plus MFCC, that was the best we have on this corpus as we have used.
Okay, sir. And the next question is can we use transfer learning with a pre-trained model on some normal speech, and would it be helpful for this classification?
Can you repeat that? Can you use transfer learning on what kind of
normal speech? Normal speech transfer learned model. Can they do some improvements in the classification task?
Yeah, it depends on. I can't really comment because I haven't done with any other task. So it depends on what task you're using for the pre-train, for the model that you're using for pre-training, right? If there is some similarity, at least, with the kind of characteristics you're trying to capture, it may. But given that I haven't done any other experiment, I can't really comment.
Okay, sir. That's all the questions from the chat. Okay, there's one more. Is there a way to recreate the speech based on the EEG, which is, I think, I don't know what that is. I think it is EEG.
It is electroencephalogram, correct.
Okay.
That's a good question. People have been trying this, right, to capture this is what even Stephen Hawking was having, right? So again, on a small vocabulary set and a very constant environment, yes, possible. But what will be a better and easier solution, because that requires other, accessories to put up and all. The better solution is with the eyes. So if you can, this is what this ALS association is talking to. They're saying that can you put, you can put some device here. When you're moving your eyes, they can pick up how you're moving. So the pattern of eye movement can be used to synthesize and speak back. But with now eyes on a screen, if you have a intelligent screen, when you move your eyes, they capture the eye location, and accordingly you can do that. There are solutions, but it has to be again very specific to a patient, right? You move a patient, things go here. But if it's something here which is attached, that will be of great value. They say.
Okay, so that was the last question from the chat. I should now open it to the audience to openly ask if they have some more questions.
Sir, I had a question. What is the relevance of MFCC today? In most of the cases, the raw waveform is overplaying outplaying the MFCC features, right? If you have enough amount of data, in ASR tasks and even the task you mentioned here. So, what's the relevance of MFCC today?
I think the relevance is that it works as a baseline. So, you have to, if you claim that you have a feature which is doing better than MFCC, you have to at least compare with MFCC, right? So that's why it's relevant, okay? But nonetheless, that's on a lighter point, but MFCC, in some sense, capture both the vocal tract as well as source, right? But now, if you look at carefully, this is a generic feature, not specific to any task. So whenever you learn features for a task, it is supposed to do better, at least, if not better, at least equal to MFCC, right? So that is why I say that it comes as a play as a baseline on which you should show you're doing any better than that.
Yeah, thank you, sir. And also, like in the talk, like you mentioned MFCC and then voice removed MFCC. And then like there's another row where F0 plus voice removed MFCC. Like what's the difference between just MFCC and the fourth one, like F0 plus voice removed MFCC?
We're talking about the difference between second and fourth, right?
Yeah, yes, sir.
Good question. I mean, you should understand how MFCC captures speech. Okay, we have done some work on figuring out pitch from MFCC. If you look at how MFCC is computed, is you put these male filters, right? And then you get the energies in these filters, log, and then DCT. And then you throw away DCT coefficient. Once you throw away the higher DCT coefficient, you put back in the log spectrum, or log energies, it becomes very much smeared. So what happens is if you do not smear, rather keep all the log, if you don't throw the DCT coefficients, then if you look at, you'll find that at the lower frequencies, you'll see in the spectrum, you'll see the pitch characteristics captured, which is this harmonic structure will be present. But once you throw away this higher DCT coefficient, it gets smooth. But MFCC has some speech information we have done both through a optimization formulation using all the coefficients and in a data-driven manner by some mapping. By removing the DCT coefficient, we have tried to predict pitch. So it does good job. So essentially it captures pitch in some way, not directly. But when you present pitch directly, it is not the way MFCC is capturing. So it is not MFCC plus VRMFCC is identical to MFCC, because MFCC also captures many other characteristics of source, which are like shimmer, jitter, and many others, like HNR, right, which are not captured in F0 only. So MFCC ideally somehow encapsulate all of that, not explicitly, but in some way or the other. So that way, we cannot say F0 plus VRMFCC is identical to MFCC. I hope that clarifies.
Yes, thank you.
Sir, I had one doubt. So I saw that you went to representation learning and came back to the traditional features. Like any reason why, or do you think you will go back to more representation learning again?
Good question. Now you see, even if it is representation learning, it will be quite a large number of features. We are putting so many filters in the CNN, right? But we are looking for a simple feature which will do good, right? So you look at with only pitch, if you can get near 90% accuracy, why not? That's the whole point. And that is what I want to leave a message that we need to be aware and conscious about the problem, not be blind and learn some network, features on some network and be happy about it, right? So here we are going to the depth of the problem to see if muscle weakness is causing really changes in what part of this entire system that is creating speech or producing speech. And if that helps us to come up with a feature like a pitch, which does so good, why not use that? Now you see, in no way you can come up with pitch using a network, because you can't train or instruct a network to learn pitch from a waveform. I don't think we exist that, because we are all blind to the network. We are under the control of the network, right? We have to just give these filters and let them learn. So we are at that intersection to say we need features. We don't care about only MFCC. We need features, better features, but also simple features which are computationally easy to handle, because we have to deploy on simple forms.
Okay. Yeah. Thank you.
Okay. From audience, are there any other questions? Okay, sir. Even I had a question regarding this. Like in the previous question, you had mentioned, like instead of blindly training, you should focus on the depth of the problem here. So what I mean is, like in this beginning question, you mentioned that LPC directly cannot be used because the vocal tract may be damaged or the vocal tract model won't work. Like so, the first basic step should be the remodeling of vocal tract. Like generally, they use all-pole filter model. So, is it possible to remodel so that it accommodates the dysarthric speech as well?
Yeah, I think good that you're thinking in that way. See, I'll actually go to the direct approach. We have to look at filter. Actually, we are looking at those also. What we are after is, think of this way, right? if you look at LPC, no, Alpol is fine. I'm not saying you have to stop Alpol, but representation of that, you probably know that there is equivalent representation like log area ratios, line spectral pairs, LPC, then reflection coefficients. There are a whole bunch of them. In fact, if you look at the log area ratios, they in some sense capture the area function from the lips to the glottis. Now, what we are after is, suppose we want to capture the shape. For example, they can't really speak ah well because they have to really open their jaw, right? Ah, right? There is a ah kind of thing. Now, question is there any way you can even figure out what is the depth of the cavity max size that they achieve, even for the same sustained phoneme? Let's take a fixed sustained phoneme. So control will be able to achieve, I don't know, maybe 10 centimeter, like ah kind of thing. But if it's a patient, is it that it is 5 centimeter? Now, to answer this question, we can use the root of LPC, but then finally connect to the clinical and scientific aspect of it, the articulatory aspect of it. That will be a good way to close the loop. And I don't think there is any problem with the Alpol modeling. That's fine. But through that, you should somehow connect to the physiological parameter as well.
Okay, I have one last question. So, have you done any phonetic ablation that shows like which phoneme is more indicative, which phoneme is not indicative?
Yeah, we have done that. Yes, we have done. So, with a model like the CNLSTM, we have found that E phoneme, E and U, they do better. We have a hypothesis also. See, the E phoneme, if you try to speak, is the phoneme with least effort, like E, right? I don't think you see anything in my, so they have to just say E, right? Natural position is almost like that. But for R, these phonemes are difficult. So we find that, with the phonemes where it's difficult to produce, we get a better number in classification because patients find it difficult to produce. Good question.
Okay, thank you.
Thank you, Ritwik. So, anything more from the audience? Any more questions? Okay, sir. I think that was it. So, once again, sir, thank you for the timely knowledge and explaining it to us why such a challenging research aspect exists for the first matter. And we will surely make use of these facts, and this will generally help young researchers follow this challenging path.
I look forward to seeing that. We need to solve problems relevant to society.
Thank you, sir. And on behalf of entire IEEE NITK, happy IEEE Day, sir.
Thank you. Thank you all. Bye.